Today, I have the great pleasure to introduce Professor Yves Prairie, who is a professor of biology at the University of Quebec in Montreal. He is one of the founding members of the GRIL Research Center. For those who are not familiar, it is a multi-university research center, research cluster that has been cultivating in limnological research and education for more than 2 decades. And he was its director for 9 years. His main research focus is on the characterization of processes pertaining to carbon cycling at different scales of expression in space and time. He instigated and co-led the ENSEA's working group on the role of lakes and reservoirs in the global carbon budget. He holds a UNESCO chair in global environmental change and currently is the president of the International Society of Limnology. By the way, I think the conference is this in August in Nanjing in China. Other research interests combine nutrient biogeochemistry, statistical modeling of ecosystem processes, and more recently, he's trying to delve into physical limnology. He is the author of more than 100 peer-reviewed papers with well over 10,000 citations. Some of these papers are particularly insightful in elucidating the complex interplay between physical, chemical, and biological processes that shape lake dynamics. Without further ado, Yves, the stage is yours.
Thank you, George. Can you hear me through this? Yes? Yes. Or maybe I'll try to be around here. Thank you, George, for this introduction. I have to say that when George contacted me by email to invite me to this conference, I very rapidly accepted because I was thrilled to have the opportunity to interact with a scientific segment of our scientific limnological community that I've not had many occasions to in the past. So I quickly accepted, and then I had a little voice over my shoulder that said, Yves, the reason you have not interacted is that you don't work on Great Lakes. And then I went into a kind of quiet state of panic, since I would have nothing to offer to this audience. So then, in my state of panic, I decided, okay, maybe I can, fake it, and this is one of my favorite lakes, and I can just scratch the scale. You won't know. I can turn it around, and it kind of looks like Lake Ontario. But I figured that you guys wouldn't be fooled. But then I realized that perhaps it was my once-in-a-lifetime opportunity to make small lakes great again. Jokes aside, there is a similarity between those of us working on small lakes and those of us working on big lakes. And of course, there are very big lakes, but there's very few of them. So on the left, you have kind of the size distribution of all lakes on planet Earth. Yeah, that covers about 3.6 million square kilometers. But in the middle graph, you have the area occupied by different size classes of lakes. So clearly, the Great Lakes are over here. And I typically work in that size range. But, in terms of area occupied in the world, they're about the same. So I think we're okay. We can understand each other. And moreover, I was, as George mentioned, I was involved in this group that we had at NCs. And one of the critical problems that we had, well, at the time we didn't even know how many lakes there were and what area they really occupied on the globe. But we had this problem of trying to upscale measurements that were done on lots of lakes, but still a very tiny, minute proportion of all the lakes that exist. And this is about a little bit what I'm going to be talking about. Of course, the numbers of the original graph have all changed. So the number, this is the amount of carbon that lakes are supposed to receive from the terrestrial world. And so in the original paper, we were at about 1.9 or 1.6, if I remember correctly. And now this is a paper that just came out a couple of weeks ago, and now we're at 5.1 petagram of carbon. But I will suggest to you that the actual precise number of this is not particularly important. Why? Because it's not like we discovered a new source of carbon that the atmosphere hasn't seen. It has always seen that carbon. But what was important in this is that it was a sufficiently big number that in between the two last IPCC assessments of the global carbon budget, all of a sudden, lakes appeared. There's no lakes in 2007, and all of a sudden, in 2013, lakes appeared. And that's because there was now evidence that the amount of carbon being processed by lake was sufficiently large to be included in there. And I would suggest also to you that the reason I am continuing to be very interested in this is that because it's a large number, then we have to be concerned about trying to predict how it will change. If it was a small number, doubling a small number still remains small. If you have a big number, if you double that number, that makes a significant difference to the globe in terms of global carbon budget. So it is more important in that sense than the actual precise number of how much carbon is being processed by inland waters. Of course, it is as well important. So I'll try to talk about various aspects of the carbon cycling, but one thread that I want to try to follow is how do we go from studying small systems, or if you are working on a big system, to have, you may have 50 stations on your large lake, but is that enough to really upscale to the lake as a whole? And we have the same problem with small lakes. We may be sampling a couple of hundred lakes, but does that say anything about small lakes as a whole? There are literally millions of lakes. Just in Quebec, there's 1.2 million larger than 0.5 hectare or something like that. So that's a lot of lakes to be sampling. So it is this upscaling problem that I want to try to address a little bit today. Now, the best way that I try to organize this is going through a little journey of carbon from land to sea and to the atmosphere as well. So I'll begin by talking about organic carbon loading and in-lake transformation, and then talk about carbon gas, production losses and emission, and how much this is changing. Okay, so let's talk about carbon loading from streams. First of all, it is fairly obvious when you look at a brownish-looking stream that it's full of organic carbon, dissolved organic carbon, which is clearly a remnant of terrestrial primary production that is incompletely decomposed, and that's what's washed away to the streams and eventually to lakes. The same thing, by the way, can be said to inorganic carbon. The amount of alkalinities, the carbonates and bicarbonates, the vast majority of that comes from terrestrial primary production that was decomposed in the soils and then created a lot of CO2, and it's that CO2 coming from soil respiration that is interacting with the minerals and creating most of the alkalinity, except in really carbonate-rich systems. So all of what lakes receive, not all, but really a large proportion of the carbon lakes receive is in fact the remnant, the product of terrestrial primary production washing into our systems. Now, to me, one fundamental insight came, well, it's kind of a notion that was there for many years, but we didn't know what to do with it, is the idea that DOC is a soup. DOC, dissolved organic carbon, is a soup of a large number of molecules, and each with their own reactivity. But how do we actually deal with that? And even though the idea was there, we didn't know exactly what to do, and it's only recently that we've been able to actually look at this in a much more defined way. I have just lost a graph here on the right. That's too bad. Never mind. On the left, and this is thanks to new analytical techniques like this FDIC-RMS that can really pull apart all the different molecules that are in there into 5,000, depending on the size of your magnet, which is the big round thing in the back. You can pull out 10,000 different molecules. You don't know exactly which compound they are, but you can know very precisely their chemical formula. So how many atoms of carbon, hydrogen, et cetera, et cetera. So on the right, there was a nice Van Kevelen diagram with the thousands of molecules from one samples shown here in a biplot of OC to HC ratios. Okay. With the advent of these techniques, some colleagues from Uppsala in Sweden could locate what is the degradation rate of each of these individual compounds. And this is what you have on the left, basically. Yes, there are a few that are created during an incubation, but the vast majority, I think it was 85% of them, show decreasing, which is what we would expect. Organic matter is being degraded. And this is the upper panel here on the right is simply the distribution of the decay rates of each individual molecules in these water samples. And at the bottom here, it's basically the same graph, but this was the same water that was irradiated with UV. And what you see is that this is a slight increase in the overall reactivity of those molecules, the overall ability to be degraded by microbial organism. So the idea that DOC is not a homogeneous soup, but rather a very heterogeneous one, to me explains a lot of the problems we had. And this can be modeled relatively simply in what we call the DOM reactivity continuum. And basically, you can look at the decrease over time of DOC by this little model, where alpha here is the average lifetime of the more reactive compounds, and the exponent mu here is a dimensionless parameter describing kind of the relative abundance of recalcitrant compounds. Okay, where am I going with this? Well, if you do the first derivative of this, you can show basically that the reactivity or the degradability of this DOM will decrease with time, which is described here in this little graph. This is very interesting, but what do we do with this in the sense that lakes are not incubations? Lakes are continually replenished with new organic carbon from their watershed. So we've combined this little model here with the idea that, well, each lake has its own water residence time, but when we talk about residence time, we really talk about the average residence time. But that means that there's lots of parcels of water that are younger age, some that are older age, etc. So we've combined these two things together and just producing a little equation like this. That's not very important. And basically that says that what you see as the degradability of the DOM in a lake is not only a function of the source material, but also of the water residence time. So there's this strong interaction with hydrology. And this has consequences. And this is, for example, two curves showing if you have the same amount of DOC coming into a lake or coming into lakes of different water residence time, so the x-axis here is the water residence time. So if you think of that DOC of having a fixed reactivity, well, this is what you would expect the fraction of your DOC load that would be turned into carbon dioxide, that would be degraded and mineralized. If you think of it as a reactivity continuum, well, the longer the residence time is, then yes, you will increase the fraction, but not as fast as it would otherwise. Why? Because you have exhausted all of the rapidly degradable molecules already. So this is a very different view of how DOC is being degraded. And this has obviously large consequences in terms of the mass that will be degraded of DOC. For example, from here to here, there's almost a twofold difference in terms of the fraction being oxidized or degraded. So that means there will be more or less of that degradation that will be turned into CO2 and back to the atmosphere. And thinking in terms of DOC, actually, before I go into this, I just wanted to show you a little application of this idea that the difference in degradation rate between lakes, of the DOC of several lakes, can be modeled very easily with this. This is just a small, this is in the eastern township region of Quebec. That's about 100 kilometers east of Montreal. And we have a reasonable relationship between DOC and water residence time. So it declines and it fits with our general conceptual model. But I could fit any, mathematically I could fit easily a curve to this, an exponential curve or something like this. But if instead I fitted this kind of model, then I get this, this curve here, which would fit as well as any other exponential decay, for example. But we get information. We get information as to what was the degradability of the original source material, in the sense that all of these lakes basically received the same, the nature of the DOC that they received was more or less the same, but the degradation expressed in each lake was really a function of the water residence time and of this reactivity continuum. So, for example, if we compare these values to that was derived from a student in our group, Dominique Vachon, there's large differences in the degradation parameter of that source material, of that source DOM material. So this is kind of the lifespan of easily degradable material. So it's much shorter in the Laurentian and much longer in the townships. So this is an example of a way that I think we can go back to try to examine, for example, okay, why is the nature of that organic matter different in those two regions, which will probably have to do with some soil characteristics. One is on the shield, and this is off the shield on sedimentary area, so perhaps that has something to do. But if we can make that link, then we can go back to other areas and really predict what's the landscape of DOM degradability that we'll have, and therefore predict at a larger scale what's going to happen without having to go and measure every lake. Now, how much of this reaches the ocean of that DOC? We now see that it's being degraded along the way, but the DOM reactivity continuum also kind of cleared a conundrum that I had that I could never quite understand, is that if you look at the export coefficient, so that's the amount of DOC per unit catchment area around the globe, but you can see that even in a really large watershed, it's lower, which you would expect, because you had the downstream end of it all when it reaches the ocean, but it's not so different than mid-sized catchments. And that's because all of the really reactive molecules have been degraded already, and that last bit between the mid-size and all the way to the ocean, well, not much more is being degraded along the way. Okay, so that was my first example. My second example follows the first one, in the sense that if this DOC is being degraded, it's being degraded to carbon dioxide, and therefore there should be a link between dissolved organic carbon and CO2 flux, or a measure of flux like partial pressure, like PCO2. There should be a relationship between the two. And indeed there is. I think the first one that was ever published was from Diane Hope in 1996 and in Wisconsin lakes. And then there's many others. So this is a kind of a compilation that we did some years ago. So it's variable. This is one we had published from lakes in the north. And this is one that was published more recently by Jean-François Lapierre, again putting together. And you can say, okay, there's a vague relationship, but it really varies between one region to the next. And one wonders now, I feel that these graphs is more or less like a game of pick-up sticks. But can we put some order into this so that we can explain the differences that maybe exist among the regions? That would explain why we get so different lines between DOC and carbon dioxide. So if you look at a lake and you think, well, let's conceptually put this. So we have DOC being degraded. That's a source of carbon dioxide. We probably have a hydrologic input of carbon dioxide itself, either through surface runoff or through groundwater input. So that could be a possibility. And of course, we'll have evasion at the surface. Now, if I turn these three processes into mathematical terms, basically you have one first component here, which is simply the degradation of DOC, modeled as a decay rate, more or less like what we just talked about. There's an input of groundwater, and there's evasion at the surface of the lake. Now, this is really basic when you think of it. But if you solve this at a steady state solution, you can turn this equation into this. And then it becomes very clear that DOC and PCO2 should be related and should be, in fact, linearly related, because this is a simple linear equation. And not only does it explain that should be a relation between the two, it explains that it should vary or not among regions, and there should be a lot of scatter in those relationships. For example, if you have a groundwater source that is more or less uniform in an area, in a region, because of the geology or whatever, well, this will tend to align the dots, if you wish, on a single line. And the fact that there is differences in the degradation of DOC because of water residence time, for example, and ZML here is just a mixed layer depth, and K600 is just a measure of the gas exchange velocity at the air-water interface, then you can understand right away that yes, there should be a vague relationship with DOC, but it will have a lot of scatter because of these differences, and you can have regional signals that are embedded in there. So that's another example to me where we have to, maybe I should tell a little story now that I think about this. I was born and raised in a scientific family of very strict empiricism. I was a student of the group at McGill with Jaap Kalf, Rob Peters, Frank Rigler, and I am very much still a proponent of that approach. But I think as I grow older, I see the real need to develop a consistent framework that we can go from one small system to a large number of lakes, that we don't have to make just a leap of faith, that there is understanding in between those two scales. Sorry, closing the parenthesis here. And well, this model, as I said, can be applied to single lakes or lakes to a region, et cetera, et cetera. And this is just to kind of wrap up that little section here. This is a survey of what we've done in about 300 lakes scattered around Quebec. Some are going far north. And basically, In terms of carbon dioxide, the vast majority, about 90% of them outgas, and about 10% in-gas, largely due to eutrophication. Okay. The same story can be told actually for streams as well. And the only point I want to make here is that the connection between the terrestrial, what happens in land and what's happening in water is even more obvious. This is, think of this as the amount of carbon dioxide that is emitted by streams, and we know now that there's a lot of carbon dioxide emitted by streams, more than from lakes. And the baseline is really driven by the NPP, the net primary production, the terrestrial net primary production of that area. So there again, there's really a close link between the terrestrial world and the aquatic world, and this is also a way to upscale to the region. I forgot perhaps to mention that the excuse me, that the original graph when we build the global role of lakes is basically just an accounting exercise. We take the mean and we multiply by the area. Well, we need to go much further into this. Okay, let me talk a little bit about methane. Methane is a much more complex gas than carbon dioxide. It's much more potent. There's less of it, much less of it, but it's much more potent. The latest IPCC equates 1 gram of methane to be equivalent to 34 grams of CO2. That's over 100 years horizon. I think that's kind of wrong. The methane stays in the atmosphere about 8 to 9 years. And in that scale, it should be more like around 100, but let's leave it at 34. And it's more complicated because it's largely produced in anoxic environments. And it is really hard to measure because it is spatially and temporally extremely heterogeneous. And on top of that, you have another group of bacteria called the mob, for methane oxidizing bacteria, that will be consuming that methane that is produced by the methanogens. So all of this makes the story very more complex. And just an example of the complexity is a series of lakes near Montreal where in every lake there's about a 4 order of magnitude difference in the profile of a single lake. And it's not even monotonic. It's not just going to decrease. It decreases and then increases again. Just to give you an impression, a visual impression of the complexity. Now, methane is found everywhere, in every system. There's not a single aquatic system that I've sampled that is not oversaturated with methane. And that's a problem. And that's a problem for the following reason. First of all, methane is produced, or is thought to be entirely produced, in anoxic environments. Well, these are all surface water measurements. In surface waters, there's not many anoxic environments. It's all oxic. It's in contact with the atmosphere. So yes, you can accumulate methane in the bottom, but really the only place where it's anoxic in the surface waters is where the water is in contact with the sediments, with the littoral sediments. So for that methane to be evaded, so it has to move in and it has to be evaded at the surface. But in that layer, there's also lots of oxygen. So you would think that the methane oxidizing bacteria would take care of that. But yet, we see methane everywhere. And this is just an example of what that fringe source would be in lakes of various sizes. Okay. So that has led to the idea of the methane paradox. The methane paradox is, why is there methane everywhere when there shouldn't be? It's the case in the ocean, it's the case in lakes, and there's various hypotheses in the ocean. It's thought that it's a byproduct of methyl phosphonate that is used up, that is reduced, and that produces methane. And this continues in the freshwater world as well. Now, let's look at how far can we go with the idea that it all comes from just from the littoral sediments. If that's the case, then the concentration of methane should be inversely proportional, well, to the square root of the surface area, simply by geometric argument. Your perimeter to area ratio decreases as you go bigger. So it's the same argument here. But this idea also has very specific implication about what should be the pattern within a lake, the pattern of methane within a lake. So imagine this is a cross-section of a lake. So the methane source is on the edges. Sorry. And then as it moves towards the center, some of it will be evaded at the surface. And therefore, we should see a decline from the shore to the center in terms of concentration of methane. Yeah, so we've modeled this, and I will spare you these equations. We've modeled this into two different configurations, assuming that the lake is round or assuming that the lake is very long and thin. And this will give you two different solutions to that equation. But the math is not important here, although it took me a long time to figure it out. But basically, the result of this is that, okay, physical transport is enough to bring the methane from the shore to the center in small lakes. You will have less. This is a distance from the shore. And you will have less, of course, in the center, but you will still be able to see it. Well, if you go into a slightly bigger lake, you've lost half of it already, and you get the point. At the 500 square kilometer, there shouldn't be any methane. There's no way the physical horizontal diffusion forces or speed is fast enough to bring it before it is evaded to the atmosphere. Yet we see methane everywhere. So let's look at the prediction of this model and how it fits to the reality of things. This was our prediction about interlake prediction. So it should be smaller in larger lakes. And yes, it is. It declines very rapidly with area. And the prediction from geometric argument was that it should be proportional to with a slope of minus 0.5, and it's pretty close, minus 0.43. So this gives credence to the idea that it's really a lot of it comes from this donut or this perimeter littoral area. Now this is a bunch of lakes where we've done this, and we see indeed this decline from shore to center at different rates, and that's expected because of the physical factors that are in there. But what we see generally is using reasonable physical parameters that we think we have constrained fairly well, the model always predicts that it's going to disappear before it actually does disappear. This is an example of a small lake here, quite a bigger lake here, and I lied at the beginning because we had one excursion into a Great Lake, which was Lake Ontario once. So this is my contribution to Great Lakes research. and we see again this decline. And Lake Ontario is 19,000 square kilometers. From physical forces, there should not be any methane in the middle. Yet there is, that's in the middle there, and the horizontal line is what should have been simply because of atmospheric equilibrium. So we're quite a bit above atmospheric equilibrium. So, okay, so what's the problem here? Where does it come from? We need a new source of it. So we used stable isotopes of carbon in the methane to try to tackle that question. And basically, if there is no other biological process acting upon this methane, then there should be no change in the signal. So basically, this is, again, distance to shore. This is the delta C13 of methane. And if it's only physics doing the movement and bringing stuff, there should be no relationships. It should be the same. If there is a strong oxidation, it should go up, and if it's strong production, because there's this idea that even though the paradigm is that methane is only produced in an anoxic environment, there's more and more evidence that it's also produced in anoxic environments. And it should predict the opposite trend in terms of C13. And then we've done this on a number of systems, and for the vast majority of them, we have seen signs of in situ production of methane in the oxic water, surface waters of those lakes. There's some exceptions to that where oxidation is the kind of the predominant biological force. Where is Ontario? Ontario is here. Also signs of production there. Okay. And this is a student of mine who's just finished his thesis, and basically he's kind of estimated production of methane in a series of lakes, and we see that it is really related to the trophic status and the amount of DOC. Okay. I think I will skip that. He's also looked at methane oxidation, and that too is a function of DOC. Because that was one of the conundrums, is that why aren't the methane oxidizing bacteria getting rid of it? And it turns out that in low DOC water, when it's clear, the methanotrophs are actually inhibited by light. So the oxidation is actually very small in those clear water lakes, and it can only operate in darker lakes. Okay. Now let's look into the future a little bit. I made the point earlier that the actual number is not, of the global number, is not very important. We only need to know it's a big number. Okay, that's true, except that there can be changes in the number that are associated with various factors. First of all, we can think of changes that or environmental factors that will change the rate of emission of the lakes. So we're going to bring the lake signal up. And we can also build more lakes. And this is what actually we do when we create reservoirs. This is the number of reservoirs, of large reservoirs from the IAGLR database. 60,000 dams, but there's a lot more than this. There's over 100,000 just in China. And this is a map of about 7,000 reservoirs of the largest size. So I think the minimum requirement here was 0.1 mega cubic meter. Okay, and there's lots of future dams being planned. These are the new dams that are either under construction or planned, and a lot of it is in places like India and China, and also a lot in South America. Now, what happens when we convert a river into a reservoir? Of course, we flood the area, and there's this new source of organic matter. So we stop the terrestrial sink, and we turn that into a lake, and then we are experiencing the degradation of that organic matter that was in that area, in that landscape. So we develop models to try to predict greenhouse gas emission from reservoirs. So we gleaned the scientific literature for all we could find that was measured greenhouse gas emission from reservoirs, and we were able to collect about 230 data points. Then we extracted all kind of information about those systems from global GIS sources, and then we tried to discover the patterns. And I'm not going to go into all of this, but basically we were able to calculate or to develop kind of simple empirical models of CO2 emission, methane ebullitive emission, so methane bubbles coming up, and diffusive emission of methane from a variety of factors. And I'm just showing you here a couple of graphs. A lot of it has to do with the age of the reservoir. When you have recently flooded a reservoir, you're going to have a pulse of both methane and carbon dioxide, but it's going to be a function of where you are on the globe with temperature and also how much carbon there is in the soil underneath it. And this is the same sort of thing for methane diffusive emissions. Now, we've built this into an online tool, so anyone can go and access the tool. You can even use this to, of course, estimate the greenhouse gas footprint of existing reservoir. You can even do it for planned reservoir. You just put your dot on when you want to put the dam and tell how high you want to put the dam. It's going to flood the area and calculate from the local characteristics the expected greenhouse gas. Now, I don't want to talk about this today, but simply to say that we've used this and applied it to this database of nearly 7,000 reservoirs to try to see, okay, how much reservoirs have added of new greenhouse gases from aquatic systems. And this is truly new ones. The atmosphere didn't see that before. And our current estimate of the global extent of reservoir is around 350,000 square kilometers. That's about 10% of all inland waters. And if you do that, you can decompose it on diffusive, bubbling, degassing, which I won't go into the details of this, and decompose it also into climate regions. And of course, as you go towards the tropic, it's warmer, you get more of it, you get more of both. But then if you do that and then scale that up to the globe, then we find this kind of numbers for both CO2 here and methane. These are all expressed in teragrams of carbon dioxide equivalent per year. And these are the previous numbers. And of course, a lot of the variability has to do with the area that is supposedly covered in those various studies. I think this one was really large because it included Lake Superior as a reservoir. Okay, there is a dam. Okay, yeah, regardless. The best number now, there's a convergence now in the numbers that are thought to be representing the global area. And this is the methane footprint, and basically it corresponds to a 7 to 10% increase over natural lake emissions. So about in line with the increase in surface area provided by reservoirs. And yes, one point I wanted to make here is that our approach here to upscaling, and this goes to one of my themes today, is that instead of just using averages to upscale to a large area, here what we are doing is what we call kind of spatially explicit prediction, in the sense that we predict the behavior of each individual system and then sum those up to get to the final number. Okay, and my last example of this, is to look at how natural lakes, how their role have changed, and there's lots of reason to expect them to change. We are warming surface temperature. Everything is temperature related in terms of metabolic activity in lakes. We have earlier ice breakup. The temperature dependent ice duration is decreasing, and therefore, for example, you will be more likely to have anoxic time periods or longer anoxic periods, and therefore more methane production, et cetera, et cetera. So there's lots of reasons to believe that the role of natural lakes will also change with time. Whoops, it's going on its own too fast. So we did this upscaling exercise onto the boreal lakes. I wonder if I can go back. Yes, of the boreal lakes of the world, and that represents the 28% of the continental water lies in the boreal zone, with about a third to a half of the world's carbon. And as I said, it's typically done, these upscaling exercises, as simply the observed average and scaling up with the area. But instead, we've again tried to make predictions onto each individual systems and then summing them up. So we use several different models that were out there in the literature, using different variables, and we've used other sources to predict or to inform as input variables each of these ones using globally available data set. And basically, what we've done here is look at, okay, what if we increase temperature by 1 degree Celsius or 2.5 degrees Celsius? And this is basically what we're showing here, is that in light blue is the current predictions, in pink is +1 degree, and in purple it's +2.5. And we've decomposed the methane emissions here as to diffusion, ebullition, and total. And basically what we get is that over 50 years, there will be an increase of 24% in methane emissions from natural lakes without changing anything else. Now, there's a lot of other things that are being changed, and Tonia de Sontro, our former postdoc, just published a paper showing how eutrophication is really changing the methane production. Probably more importantly than temperature is. But I won't go into that. I will let her speak to this. Okay. There should be a slide before that. Yes. Concluding remarks should be before the acknowledgement. Okay. Basically, I guess what I wanted to convey is that the story of carbon cycling and how it leads to carbon emission is not over. And it's important to build models that are consistent across spatial scales so that we can really do this upscaling appropriately. And this is particularly important in view of trying to predict what will be the future role of lakes in this global carbon cycle. And with this, I will thank you for your attention. I'll take any questions you may have. I don't know. I don't work on large lakes. I really don't. Sorry.
Any other questions? Yeah.
10 years ago, there was a series of papers proposing that atmospheric carbon might be mitigated by sequestration in freshwater lakes, and that seems to have been debunked a bit. And we've also found that increased carbon might lead to a ratio of decreased calcium in lakes. Could you comment on that?
Well, that solution would be then that if we take their argument to their extreme, we should be eutrophying lakes, because that's the only way they're going to start capturing CO2 is if we eutrofy them. But the flip side of that, of course, is that you're going to be converting a new source of carbon to the sediments into fuel to make methane, because in eutrophic system, you will have a lot more anoxia because of higher respiration rates, and then you will be turning this into methane, which is at least 34 times more potent. So I really don't think that's a viable solution, for sure. Well, that's an interesting question, Lou, because I happen to be part of an IPCC working group on exactly this. And we have just finished a second-order draft of a new chapter, a methodology report, that if it goes to all the political stage, we're just the lowly scientists doing the work, but it has to be approved at the higher levels. if it is approved, and we're hoping it will be approved, that means that all the countries that are signatories to big climate agreements will have to account for greenhouse gas emissions from reservoirs in their annual inventory of things. So some countries it will have no effect, some countries it may have a big impact. That's now, that's a good one. It's definitely related to primary production. I mean, we see it in the way we've calculated it from mass balance. Basically, you take all the known sources and all the known sinks, and you put them together, and then you realize, okay, that doesn't fit, we're missing a source. And this is how we approach the problem in our small lakes. And we see a very strong correlation with total phosphorus, total chlorophyll, etc. We even see it on a daily cycle. Like it turns off when the light is not there, and it turns back on in the morning. So it's clearly tied to primary production going in the lake, but the actual kind of a geochemical mechanism in there, or more like the biochemical pathway of the cells, that we don't know. I'm thinking aloud here. Well, it will change a bit the hydrology, but I think most importantly, it will change the organic carbon loading to lakes. And I've never quite understood this, but everywhere I've looked, increased precipitation leads to higher organic carbon loading. It's not like it seems like almost there's an infinite source of organic carbon in the soil, and if you have more water to flush it out, more of it will come out without being exhausted. So this will have an impact on various aspects of carbon dynamics. Will it increase the oxidation versus the production side of methane? I'm not too sure. But well, for carbon dioxide, I would guess it would increase the footprint of lakes by increasing the carbon loading.
Any other questions?
There's one over there.
How is the recovery from gas affecting the carbon?
Interesting, because we have a bunch of students that just went off the field this week in Ontario, where we're measuring a lot of the lakes, of the carbon footprint of the lakes that were acidified, really strongly acidified and recovered. And the idea is to look exactly at that, what's the impact on that. So I cannot comment at this point, but maybe in a year.